Hello, and welcome back to another episode of 7 Minutes of Circuits. My name is MSiegel, and I'm a junior in the Electrical Engineering program at CSU, and I'm currently enrolled in ECE 311, Linear Systems Analysis, ECE 331, Electronics Principles, and ECE 341, Electromagnetic Fields and Devices. Today, we will discuss the audio back-end system or amplifier of a generic smartphone, and how it relates to concepts learned in each of the 3 junior year ECE courses. Let's begin with the 311 perspective of the system. For this, we can assume the audio amplifier is a linear time-invariant system, or LTI for short. A linear time-invariant system passes a signal through relatively unchanged. You can see this relationship in the equations describing the input and output seen here. The only parts affected are the magnitude and phase of the signal. In the case of the audio amplifier, the magnitude is greater than 1, so the output is larger in amplitude and therefore power than that of the input. The magnitude of the LTI system's effects are also dependent on frequency. From the equation describing the frequency response of the system, h of j omega seen here, you can see that as the frequency increases, the magnitude of h of j omega approaches 0, which results in attenuation of the higher frequencies. This is analogous to a low-pass filter which passes low frequencies while removing high frequencies. Now let's switch over to the 331 view of the audio amplifier. Here you can see the circuit schematic of the audio amplifier. To help with our analysis, we can represent the speaker as a resistive load in parallel with a capacitor seen here. The diagram shows that MOSFET M0 is biased by VDD with a 5 kilo ohm resistor at the drain terminal and by VB at the gate terminal. Biasing the transistor allows it to operate at a specific point in its IV characteristic curve, seen here. This allows the transistor to match the specifications needed of the circuit and operate in a way that is most useful for the application of the circuit being designed. Next, the output from M0 is sent to M1 and then to the speaker. If the speaker, or load in this case, is connected directly to M0 instead of M1, then some of the power is lost through R1 as it goes through the circuit to pass to the speaker. The circuit is thusly inefficient. Having M1 as a second stage allows the output power from VDD to drop directly across the speaker, resulting in full amplifying power and full efficiency of the circuit. Now that we understand what the amplifier does to the input signal, let's see what the speaker does with the output signal and how it makes sound, all from a 341 electromagnetics perspective. I will note that there are electromagnetic fields at play inside the amplifier circuit due to currents flowing through the wires, for example, but these fields are so weak and small that their effects on the circuit are almost undetectable, and therefore we can ignore them completely in this case. So how does the speaker turn an AC signal into sound? To find that out, we must look inside the speaker. Here you can see a diagram of a basic speaker, and inside you can see a coil of wire called the voice coil, situated right near a permanent magnet. The permanent magnet has an associated magnetic field that extends from the North Pole all the way around to the South Pole. When a current is passed through the coil of wire, a magnetic field is also produced inside the coil of wire that is either repulsive or attractive to the magnetic field of the permanent magnet. Since the voice coil is connected to the speaker cone, which can move, the speaker will move back and forth proportional to the current flowing through the coil of wire. When the speaker cone oscillates, it creates sound waves, which is how a speaker converts an AC signal into sound, all by using electric currents and magnetic fields. Combining the lessons we've learned in each of the 3 junior year ECE courses, we were able to fully describe the audio amplifying back-end system of almost any smartphone. This is also similar to any amplifier seen for any kind of audio applications, including your stereo at home, or a car stereo, or a car subwoofer amplifier. I want to thank you all for your time, and I hope you've enjoyed today's presentation. We'll see you on the next installment of 7 Minutes with Circuits. Have a good day.